photoelectric effects experiment has been discovered by Heinrich Hertz in 1887. So during that time, we cannot use any the classical model such as the mechanics or the electromagnetism to answer or to understand this type of the experiment. Okay, but then 17 later, the Albert Einstein can describe this experiment using the idea of the quantization of the electromagnetic wave or just photon. So the experiment is here. So we have a detector and the metal surface. Detector and the metal surface is inside the vacuum chamber. Okay, and also detector and the metal surface here are connected to the battery. Okay, so the variable power supply. So it means that we can change the voltage of this power supply here, and then we can measure the voltage of this power supply using the voltmeter. So now if we shine the light, okay, actually it should say that if we shine the electromagnetic wave, it can be the visible light, it can be the infrared, or it can be the UV and etc. Okay, so if we shine the electromagnetic wave from here and then to hit the metal surface, the experimental result is the electron will come out from the metal surface here. So now this electron just called the photoelectrons. Okay, so it's be the electron emitting from the metal surface by shining the electromagnetic wave. Okay, so it's just called the photoelectrons. Okay, and then also the kinetic energy of these photoelectrons, so K, okay, is going to be less than or just equal to the maximum kinetic energy. So it means that we can have the broad range of the kinetic energy of the electrons, but the maximum value of this kinetic energy is the K max. Okay, so I mean later I will explain how we can find the maximum kinetic energy, and I will explain why we have the broad range of the kinetic energy of the electrons. Okay, so let's talk about this one later. Then this is the classical prediction. Okay, so we expect that the results should be something like this. Okay, so the first one, there would be a significant time delay between the moment of the illumination and the ejection of the photoelectrons, as the electrons absorb the incident energy until their kinetic energy was sufficient to release them from the atom's grip. Okay, let me explain. If you use the classical theory, right, to explain this stuff, it means that the light, we have some energy. Okay, when we shine the light to the metal surface, so don't forget that the metal, you have the electron, right? Okay, we have the free electron. So now when this free electron gets the energy from the light, so it will absorb the energy of the light. So if the energy of the light is just small, so electron will get the small energy, right? So it means that it's gonna take some time to accumulate more energy and more energy until his energy is sufficient enough to be released from the metal surface here. Okay, so that's gonna be the idea how we can use the classical model to explain this one. So now number 2, increasing intensity of the light would cause the electrons to leave the metal surface with the greater kinetic energy. So we said that, okay, the light has some energy. So if we increase the intensity of the light, it means that the light will have more energy. Okay, So then when the light with the more energy incidents on the metal surface, then the electron will gain the more energy as well. So when the electron released from the metal surface, if you have the higher kinetic energy, okay. So that's will be the explanation by the classical model as well. Now number 3, the photoelectrons would emit regardless of the frequency of incident energy as long as intensity was high enough. Okay, so it means that if we charge the electromagnetic wave with maybe the frequency from the radio wave and then to the gamma ray, right? So you can see that the frequency of the radio wave is very small, and the frequency of the gamma ray is very large. Okay, so when we just charge this metal surface with this type of the electromagnetic wave, we should see the photoelectron as well. Okay, this is the classical prediction. And now the last one, there should be no relationship between the frequency of the light and the electron kinetic energy. The kinetic energy should be related to the density of the light. Okay, so this one is related to number 2 here. Okay, but now let's look at the experimental results. Okay, let's consider this simulation from this website. So we have the light coming from this direction and then hit this metal surface, right? And then the electron will be released to another surface here, okay? And then we have the loop, right? And then we have this ammeter. So it means that we can measure the current by this movement of the electron. And now let me just make the voltage of the battery equal to the 0 volt first. Okay. One thing that you can notice is, so when we just shine the light to the metal surface, electron just pop up. Okay, so that's be the first experimental result that we can get. When we just shine the light to the metal surface, electron just pop up. So it means that it doesn't need time to accumulate the energy. Okay. So this will be the first experimental results. So electrons are emitted from the surface of the metal almost instantaneously, so less than 1 nanosecond. So nano just 10 to the negative 9 second, right? So less than 1 times 10 to the negative 9 second. So it's just very small after the surface is illuminated. Okay, so now you can see that these experimental results, the first one, it just disagree, right, with the classical prediction here. Okay, so now let's look at number 2. Okay, so now we just want to increase the density of the light and see what happened. It should be somewhere here. Okay, so let's just start from 10%. Okay, you see, if we have the density about 10%, right, we have just few electrons coming out from this metal surface. But then if we increase the density, so let's say the 90%, we have more electron, right, coming out from the metal surface here. Okay, so the experimental result that we can get from this picture is, if we increase the intensity, we get more photoelectrons. Okay, but then how about the kinetic energy? So now this kinetic energy can be measured using the current. Okay, so let's say if we have 90%, right, we have the current equal to the 61.5 nanoampere. But then if we have, let's say, 20%, oops, sorry, wait, no, sorry, my bad. Actually, to measure the kinetic energy, we should need the voltage here. Okay, but I mean, it's just called the stopping voltage. Sorry, it's not the current. So let me talk about the stopping voltage later. Okay, But one thing is you can notice from here, if we increase the intensity, right, so we get more photoelectrons. Okay. So number 2, right, increasing intensity of the light causes more electrons to eject from the metal. Their maximum kinetic energy remains unchanged. Okay, so the maximum kinetic energy doesn't change. The thing is changed is the number of the photoelectrons. Okay, so again this number, this experimental result, right, just disagree with the classical prediction. Okay, so now number 3, we said that the photoelectrons would emit regardless the frequency of the incident light, of the incident energy, right, as long as the intensity was high enough. Okay, so let's say, so now let's just change the wavelength. Let's just change the wavelength here. Okay, let's try the lower frequency. So it means that the wavelength should be longer. Let me just try from 250 nanometer. This is the small wavelength of the high frequency. Okay, but then if we increase the wavelength, or if I just decrease the frequency of the incident light, let's say 530. So you see, there's no photoelectrons emitted from the metal surface. Okay, let me try the shorter wavelength or the high frequency. Let's say the 4x0. Again, no photoelectrons. Let's try the 400 nanometer. Yeah, okay. So now with the 400 nanometer, we can have the photoelectrons, right? But we increase the wavelength, or if we decrease the frequency of the incident light, okay, so you can see that we don't have the photoelectrons anymore. So now let's just come back to the 400 nanometer. Okay, so now we have the incident intensity of the light equal to the 100%, right? So now let's just reduce to maybe 10. Okay, we can still see the photoelectrons. Then what can we conclude from this, right? We can conclude that for each metal there is a cutoff frequency, or sometimes just call it as the threshold frequency. Okay, let me just take a note here. Okay, sometimes just call it as the threshold frequency. We use a symbol as the FC. So the small c here just for the cutoff, okay, and the F just for the frequency. It means that if light of the frequency lower than the cutoff frequency are used to illuminate the metal surface, so no photoelectrons are ejected, okay, regardless of how intense of the incident radiation is. So now from the experimental result, you can see that if we just increase the wavelength to a value, right? On the other hand, if we just decrease the frequency of the incident light to a value, so there's no photoelectrons emitted from the metal surface. Okay, so you can see that this experimental result it just disagree with this prediction. So now the last one. There should be no relationship between the frequency of the light and the electron kinetic energy. Okay, the kinetic energy should be related to the density of the light. Okay, but now the experimental results shows that the maximum kinetic energy of the photoelectrons increase with the increasing light frequency. It means that if we reduce the wavelength of the visible light, then the photoelectrons will get more kinetic energy. Okay. So how can we use the physics model, right, to describe this experiment? We need to go back to 1904 by Albert Einstein. So Albert Einstein proposed that the quantum of the electromagnetic waves is called the photon. Okay, so now you can see that actually Einstein got this idea from the Max Planck, okay, from the Max Planck by the blackbody radiation. Okay, so Einstein proposed that the quantum of the electromagnetic waves is called the photon. So we can say that the photon, right, it's just going to be the particle of the electromagnetic wave. But don't forget that electromagnetic wave doesn't have the mass. It means that the photon doesn't have the mass as well. Okay, and then the energy of the photon particles is just equal to the h times the f here. So now this h is just called the Planck constant. Okay, I mean we have seen this one already. The Planck constant, the value is the 62626 times 10 to the negative 34, right, in the unit of the joules times the second, or in the unit of the electron volt, it's just equal to this value. So we talk about unit of electron volt later. Okay, and now the f is going to be the frequency of the electromagnetic wave in hertz. Okay, as usual. So if the frequency is high, it means that the energy of the photon is going to be the high as well. If the frequency is low, so the energy of the photon will be low. Okay, and then Einstein proposed this equation. Okay, he just proposed this equation. So now this equation just comes from the idea of let's say from the conservation of the energy. Okay, from the conservation of energy. So this equation say that the total energy of the incident photon, okay, all the total energy of the incident light is going to be equal to, okay, so now some energy will be used by photoelectrons, right, to escape from the metal surface. So it's be this one. So this energy is just called the work function. Okay, it's called work function. It's going to be the energy required by photoelectrons to escape from the metal surface. Okay, and then so if we have the energy left, right, so the left energy here, the remaining energy here is going to be the maximum kinetic energy of the photoelectrons. So it's just called the Kmax here, as we just mentioned here already, right? Okay, one more time. The energy of the incident photon is just equal to the energy required by the photoelectrons to escape the metal surface. Okay, and the remaining energy will be the maximum kinetic energy of the photoelectrons. Okay, so so this idea just comes from the conservation of the energy. But now, first of all, so what is the work function, right? The work function for the different metals are different as well. So let's look at this table. Okay, so you can see that the work function of the sodium is just equal to the 2.46 electron volt. So again, I will explain about this unit later. And for the lead, right, it's just the 4.14 electron volt. Okay, and etc. So you can look the work functions for the selected metals from this table. Okay. One more thing that I just want to mention, or just to emphasize about this equation, is this equation is 1 by 1. So what does it mean, 1 by 1? It means that if we have one photon, okay, shining on the metal surface, then we will gain one photoelectron. Okay, so to emphasize, just mean that one photon will have one photoelectron. Okay, so this question just describe this 1-to-1 relationship. Okay, so let's draw the graph. Okay, so let's look at this graph, right? If we have the frequency as the horizontal axis here, and then if we have the maximum kinetic energy as the vertical axis, actually let me move it to, yeah, maybe to here. Okay, so now I just want to draw the graph between the maximum kinetic energy and the frequency. So actually in the experiment we just vary the frequency, right, and we can measure the maximum kinetic energy using the stopping potential that I will explain later again. Okay, so let's look at this equation. Let's just rearrange. Okay, let's just rearrange this equation. Let's say that we have the Kmax, right? We have the Kmax equal to the h times the f, and then minus the work function. Okay, so now you can see that the Kmax here is going to be the y-axis, and now the frequency here is going to be the x-axis, right? When we compare to the y equal to the m times the x, and then plus the c, so it means that the gradient of the graph is equal to the Planck constant equal to the h, and then the y-intercept, right, is just equal to the negative of the work function. Okay, and then the x-axis just the frequency, and then finally the y-axis just the maximum kinetic energy of the photoelectron. Then finally we can just draw the graph to be like this one. Okay, it just look like this. So here we say that the slope of the graph or the gradient, right, is going to be equal to the Planck constant, the h. Okay, and then also this value equal to what? Okay, this value equal to what? So let's see, at this value the kinetic energy equal to the 0. Okay, let's look here. At this frequency the kinetic energy equal to the 0, so it means that this frequency equal to the work function and then over the Planck constant over the h, right, because we just move h to here. So now this frequency is called the cutoff frequency, the fc, equal to the work function and then over the h. Okay, then this graph just explains many things actually. Okay, so the third experimental results, right, we say that there is the certain cutoff frequency if the light of the frequency lower than this cutoff frequency are used to illuminate the metal surface. So there's no photoelectrons ejected regardless of the high intensity of the incident direction is. So just clear, right, from the graph, if we have the light, I mean with the frequency lower than this value. Okay, so let me separate into the two regions here. Okay, if we have the light with the frequency lower than this this value, so it should be about this part, right? It means that there's no photoelectrons. Okay, so this part, let me use this color. Okay, from here it means that no photo electrons. Okay, but then however, if the frequency is greater than this cutoff frequency, so it should be in this regime. Okay, so now you can see that we can have the photoelectrons, and the photoelectrons will have the kinetic energy equal to, I mean, the value on the graph here. Okay, so then why when the frequency is less than the cutoff frequency we don't have the photoelectrons? So it's just making sense, because if the frequency less than this cutoff frequency, it means that the energy of the incident photon, right, will be less than this work function. So it means that the electron will not gain enough energy, okay, so it cannot reach the wave function to escape from the metal surface, okay. Now, increasing the intensity of the light causes the more electrons to eject from the metal. Then maximum kinetic energy remains unchanged, okay. So increasing intensity of the light, it means what? It means that we increase number of photon, okay. If we increase the intensity of the light, it just means that we increase the number of the photon. Okay, let me take a note here. So it means that number of the photons, okay, increases. Okay, so that's the point. If number of the photon increase, but don't forget that each photon still have the same energy equal to the hf, okay. So if the number of the photons increase and then hit the surface of the metals, it means that we will have more electrons eject from the metal, right? Because this equation is 1 to 1. 1 photon for 1 photoelectron. So if we increase the number of photon, then we can get more photoelectron, okay? And then the maximum kinetic energy remains unchanged because each photon still have the same energy, okay. And now number 4, right? The maximum kinetic energy of the photoelectrons increases with the increasing light frequency. So it's just this equation, okay. So the Kmax is proportional to the frequency of the incident light. Okay, that's it. Okay, so let's consider this. So let's say that if this graph, okay, if this graph is for the sodium, okay, if this graph is for the sodium, so then what's going to be the graph of the lead? Okay, I will just let you think first. If this graph is for the sodium, right, so what's going to be the graph of the lead here? So now you can see that the lead, right, we have the wave function higher than that of the sodium, okay. Then don't forget that the slope is the Planck constant. The Planck constant is a constant, right? So it means that it's not going to change if we change the metal from the sodium to the lead, okay. It means that the slope of the graph here should be remain the same, right? Should be remain the same, okay. But the difference is this value, okay, this value. The cutoff frequency must be different because the cutoff frequency is related to the wave function, okay. So the higher the wave function, so the more the frequency, okay, the more the cutoff frequency, okay. So it means that this should be the value, the cutoff frequency of the lead, and this should be the cutoff frequency of the sodium here. Okay, now let me just talk about electron volts. Okay, let me just talk about the electron volt. Okay, electron volt. Okay, so we just use the symbol as the EV, okay, is a unit of energy. Actually, the energy has lots of the unit, right? It has joules, it has the calories, and it has also electron volt as well. But then, okay, why we need to use unit electron volts in this chapter? The answer is because the energy of the photons or of electron or whatever is very small, okay. So if we use unit of the joule in this chapter, so this unit is going to be too large, I mean, for this energy that we are taking into account here, okay. So then that's why we need to use unit of the electron volts. So we say that 1 electron volt, right, is going to be equal to 1.602 times 10 to the negative 19 joules. Oops, sorry. Okay, so does this value look just familiar to you? Yes, right? So this value is just the charge of the electron. Okay, so this will be the conversion from electron volts to the joules, right? So we just multiply with the 1.602 times 10 to the negative 19 joules, and that's it. And then one more thing that I just want to mention is we just want to find the relationship between the energy of the photons and the frequency. So we have this already equal to E equal to HF, right? But then how about the wavelength? Okay, how about the wavelength? So let's consider this one. Okay, let's say the relationship of the photons energy and the wavelength of electromagnetic wave. Okay, so let's just start from this question. E equal to the H times the F, right? And we know that the F equal to speed of the light in vacuum c, and then over the wavelength. Okay, we have the F equal to c over the wavelength. So now if we just plug in this F into this equation, so it's going to be equal to the H times the c, and then over the wavelength here. Okay, so then later on we are going to use this type of this relationship from the wavelength to the photon energy, or from the photon energies to the wavelength. Okay, so now we just want to find this value. Okay, we just want to find this value, but the first thing is I just want to describe this energy in the terms of electron volt. Okay, I just want to describe this energy in the terms of the electron volts, not the joules. It means that I need to divide this equation by the charge of the electron, right? Or just by this value. So then we have the H times the C, and then over the E. Okay, so this is these are constant, right? And then times the 1 over the wavelength. But don't forget that right now the wavelength is in units of meter. Okay, it's in unit of the meter. Okay, let me just write here. Okay, so let's just put in the value Hc over the E. Okay, Hc over the E. Okay, so the H is 6 times 10 to the negative 34, right? This is the H times the C, and then over the E, the charge of the electron, 1.602 times 10 to the negative 19. Okay, and the answer is, wait, yeah, right. Okay, let me take 4 significant figures. It's going to be the 1.240, right? 1.240 times 10 to the negative. Okay, 1, 2, 3, 4, 5, 6. Okay, so we have, it's going to be equal to 1.240 times 10 to the negative 6 in the unit of electron volt times meter. Okay, and then over the wavelength in the unit of meters here. Okay, but then we use we usually use the wavelength in the unit of the nanometer. It means that we need to convert, right? Okay, so we said that let's make the conversion. 1 nanometer. Wait. We said that 1 meter oh, sorry, it should be this one. 1 meter, okay, it just equal to 10 to the 9 nanometer. Okay, 1 meter equal to 10 to the 9 nanometer. So you can see that this unit meter just cancel out, okay, and we have 10 to the 9 times the negative 6, right, equal to the 1000. So the 1000 multiplied with this one equal to the 1240. Okay, so then finally then we have this relationship. Okay, we have that. Oops. Okay, so we have this relationship. Okay, so it means that if we have the wavelength in the unit of nanometer, then we can find the energy in the unit of electron volt. Okay, so please remember this equation because we're gonna use this one a lot. Okay, we're gonna use this one a lot. Okay, so now the next point that I just want to make is here. Okay, the next point I just want to make is here. Okay, let me move this one first. This will be the metal surface. Okay, and the atom and the electrons. Okay, the question is why some kinetic energy of photoelectrons is less than the maximum value. Okay, so why some kinetic energy of the photoelectrons is less than the maximum kinetic energy? On the other hand, it means that so why some electrons has the maximum kinetic energy which is equal to this value, right? But why some has the energy less than this value? Okay, so let's consider here. We know that in the metal, right, okay, consists of the atoms and electron. Okay, atoms will be aligned in the order something like in this picture or in this model here. And then for the metals, we have the free electrons. It means that the electrons can move, freely throughout this metal here. Some electrons will be at the surface. Some electrons will be just inside. Okay, so now when we just shine the light, okay, to the metal, electron at the surface, first of all, this one, right? The electron at the surface will gain all the energy of this light. Okay, it means that there's no energy loss of this photon. Okay, then when this electron released from the metal, right, it will have the maximum kinetic energy. Okay, so this electron will have the maximum kinetic energy. Let me just say, okay, if we have the Kmax, but then on the other hand, if we consider the electron which is inside the metal surface, right? For example, this one. So now you can see that when the light, right, just hits on the metal surface, and the light can just, penetrate through the metal as well. And then the energy of the light can be lost. Okay, so that's the one thing. And also, when this electron gets the energy, right? So if this energy just wins the work function, it means that the electron can just move to the surface and then out of the surface as well. But now you can see that there's loss of the energy loss during the motion of the electron from here and then out of the surface, right? So it means that the kinetic energy of this electron should be less than this value, should be less than the maximum kinetic energy. Okay, so that's going to be the explanation why some kinetic energy is less than the maximum value of the kinetic energy here. And then the last point that I just want to make is, how can we measure the maximum kinetic energy? Okay, so how can we measure the maximum kinetic energy? Okay, so this is going to be related to the stopping potential that I just mentioned 2 times already from the beginning. Okay, so again, let's go back, okay, to look at this picture. No, actually, look at this simulation. It should be better explanation here, right? Let's make the reference. Okay, maybe 400. Yep. Okay, so now you can see that the voltage of the battery, right, equal to the 0 volt. But now if okay, if I increase the voltage to be something like this, so you can see that this is the negative terminal. This is the negative terminal of the battery. This is the positive terminal of the battery, right? So this positive terminal is connected to the target, and the negative terminal is connected to the metal surface here. Okay, so this will be the negative and this will be the positive. It means that when the electron, right, when the photoelectron release from the metal surface here, is going to be attracted by this detector or the target. Okay, so there's no problem. But then what happens if we convert, okay, the polarity of the battery? So let's say that in this case oh wait, it's not. Yep. Okay, so let's say this. Okay, if we have this to be the positive terminal, right? So this will be the positive, and this will be the negative terminal of the battery. So this will be the negative, right? So when electron, right, emitted from the metal surface, but now you can see that this positive plate, right, must attract the electron. Okay, so it means that some electron will have the enough energy to come to this plate. Okay, so that's why we can get the current here. But then some electron won't have enough energy to come to this negative plate. So it means that if we just go to maybe a path and a position, and then attract back to this positive plate, right? For example, you can see maybe this one, okay, and go back one more time. Okay, this one and go back. Yeah, maybe this one and go back, right? Okay, so that's be the thing. But then the electron that have energy enough to come to this plate, right? So it's called, if you have the maximum kinetic energy, okay, or maybe less than, but again, the maximum kinetic energy should be enough, to come to this plate actually. But then if we increase this voltage more and more until at a point that the maximum kinetic energy is not enough, okay, to come to this plate. It means that the current of this circuit must be equal to 0, okay. So let's see, if we increase the voltage, right, so this are 0.2 volts, okay, so we still have the current here, okay. So let's increase more, 0.3, okay. So now you can see that at the 0.3 volts, right, the current equal to the 0, okay. It means that when we have the photoelectrons, right, emitting from this, it's going to go to the right hand side, but it's going to go slower and slower and slower, and then it can reach, the surface of this detector, and then it's going to be attracted back to the metal surface here, okay. So it means that the current is just equal to 0, and then this value is called the stopping potential, okay. This value just called the stopping potential. So it's going to be the potential difference that stop the movement of the electron coming to this detector, right, and the current of the circuit just equal to 0, okay. So then from this expression we see that the stopping potential, the Vs, right, okay, if we multiply the Vs, which is the potential, with the E, then we can get the EVS, okay. The EVS here is going to be the unit of the energy, okay, the same as electron volts in this case, okay. So the EVS we have given as the energy. The EVS is going to be equal to the maximum kinetic energy, okay. So this can be the way that how we can measure the maximum kinetic energy, okay, by changing the voltage of the battery here, okay, and until the current equal to the 0, okay. So that's why we can get the stopping potential, and then we just multiply the stopping potential with the charge of the electron, right, we can get the maximum kinetic energy.